Let's talk about trends in acidity. So I want to be able to look at two molecules and predict which one of them is going to be more acidic. Why? Well, I don't want to have to look up pKa's all the time, although I can do that. But also, a lot of the compounds that I want to make and deal with are new and understudied. And the pKa is not in a book somewhere for me to look up. Right? I'm going to have to look at the molecule and make a guess about where the most acidic protons are in the system. And so I want to understand trends in acidity. And the biggest trend is this. Strong acids, as I said before, have stable conjugate bases. And sometimes we say weak conjugate bases. So by stable, by weak, I mean low in potential energy and unreactive. That begs the question, how is electron density stabilized? We're stabilizing these conjugate bases by putting electron density either on a more electronegative atom or on a bigger atom or a bigger system. Now, these two are not the same, and sometimes they seem to fight against each other. So how do we know which rule to apply? Well, for the most part, electronegative atoms, when we talk about looking at the difference in electronegativity, we are talking about atoms of similar size, so on the same row of a periodic table. But when we're comparing things from different rows with each other, the size difference is massive. And that massive size difference is going to play a big role in acidity. So first, let's look across a row. So comparing acidity of CH, NH, OH, and FH, we see that we get increasingly more acidic as we go to the right. So carbon is a very, very, very weak acid. Ammonia is almost never an acid, but we've seen it be an acid a couple times. Water can be considered an okay, still pretty weak acid. And HF is a stronger acid than these, although it's not quite as strong as others. So if we look at the conjugate bases of these, the least acidic is the most basic conjugate base. You can see that this goes with electronegativity. So fluorine, we said the fluorine nucleus can pull electrons to itself very well. So fluorine is more than happy to stabilize that negative charge because it's more electronegative. Oxygen is a little bit less electronegative, nitrogen and carbon down the line. So here, if we're comparing within a row, we're going to get more acidic as we go to the right when I'm comparing CH, NH, OH, and FH. Let's actually pop out carbon because we should talk about hybridization. Hybridization can affect acidity quite a bit. sp3CH is generally a very, very weak base, or weak acid rather, at 60. But an sp2 carbon is a little bit more acidic. An sp carbon, so a triple bonded carbon, is actually quite a bit more acidic, 25. So sp alkyne carbon is actually more acidic than an amine, and quite a bit more acidic. So how should I think about this? Well, remember we talked about S character of orbitals. So these sp orbitals, and this CH bond is made from an sp orbital in carbon. Those sp orbitals are more S-like and more S character. And so those electrons are held more tightly to the nucleus. So here, the sp is actually more electronegative. So we can't really honestly talk about electronegativity of carbon like it's all carbon, because triple bonded carbon is a fair amount more electronegative than double bonded carbon, which is more electronegative than single bonded carbon. So there is a difference in electronegativity among these hybridized carbons, and so there's a difference in acidity. And sp carbon is quite a bit more acidic than sp2 and sp3. If I'm looking down a column, now I see that I get more acidic as I go down. So HF is a pretty decent acid, but HCl is actually negative, right? So that means that it is completely dissociated, and bromine as well, HBr. And we don't even need the super, super strong acids. We see this with oxygen and sulfur as well. H2S is quite a bit more acidic. Notice that this does not follow electronegativity. like we made the argument for the rows. Here, it's just about bigger atoms. So as we go down the periodic table, we get bigger atoms. Bigger atoms generally get weaker bonds, so that HBr bond is pretty weak already. But also, there's more volume in that negatively charged conjugate base. There's more volume for the electrons to spread out. Okay? So again, it's all about stabilizing electron density. We can stabilize electron density by putting it on an electronegative atom. But we can also stabilize electron density by just letting it spread out, so we can minimize that electron-electron repulsion between. Okay, so up till now, we've looked at differences in acidity where the two things we're comparing have the acidic proton on different atoms, right? We're like HC versus HN versus HO versus HF, or HF versus HCl versus HBr. So now, that's not usually what we care about. A lot of times, we're going to be comparing two things where the proton in question is bound to the same atom. So for instance, this is acetic acid. I mentioned it earlier. Its pK is around 5. It's more like 4.75. Trichloroacetic acid is a much lower pKa, 0.65. Let me complicate it a little bit more. So we just talked about how HF is not as good acid as HCl, right? So acidity increases as you go down the table. So if I compare trichloroacetic acid with trifluoroacetic acid, you might be tempted to jump to, oh, chlorine's more acidic, so this number is going to be lower than this number. Actually, no. Trifluoroacetic acid is almost a full pKa unit more acidic, 0. So why? Is this one of these exceptions that people talk about with organic chemistry? No, there's no exceptions. All right, so what we're talking about here is the inductive effect. We think about the conjugate base. The conjugate base of trichloroacetic acid looks like this. We've got dipoles over here, right? So chlorine is more electronegative than carbon, and so we've got a dipole here, a third, second, a third. All those TCl dipoles are pulling away from the rest of the molecule. So it's a pretty big net dipole going this way. What that's going to do is actually polarize this C-C bond, right? So now, because this carbon is so electron poor, it's going to be borrowing electrons from this carbon, which doesn't have a lot. But now this carbon is even more electron poor, and it's going to start to borrow electrons from this O-, and that's kind of what we had wanted, right? That's how we stabilize conjugate bases, is by spreading that negative charge out. So you can think about this a couple different ways. You can think of it as, like I've drawn here, polarizing the sigma bonds. So I have a really polar sigma bond here, a little bit less polarized bond here, a little bit less, and so forth. Right? You can also just kind of think of this as polarization through space. Right? So I've got bar magnets here that are pulling on a little bar magnet over here. And the closer I get those bar magnets, the bigger the effect there's going to be. For that reason, this effect is really dependent on distance. So the more distance these chlorines get from this charge, the less of an effect they would have, right? So if I had something like this, where I still have chlorines, but now they're really, really far away from the acidic proton, that pKa is going to be about 5. That's not going to have a very big difference. But when they're close, I can really have a pretty big difference on the pKa. And this also explains why fluorine has a greater effect than chlorine. Again, I'm not talking about the difference in strength between the HF and the HCl bond. What I'm talking about is how good are these atoms at pulling electrons toward themselves. And fluorine is better at it than chlorine is. And so that's why fluorine, even though HF is a weaker acid than HCl, fluorine has a greater inductive effect than chlorine does.